Good morning, everybody, and welcome to Physics 101. Today is the start of week 5. Week 5 is important from different perspectives. First of all, in terms of the exam, we have an exam that is due that is going to be held this week on Wednesday. So Wednesday, the exam will be opened and from 8 o'clock in the morning till like 11 p.m. So there is basically plenty of time for you guys to take care of the exam. And it's done so that it accommodates for everybody in terms of those who have classes in the daytime, whether in the high school or in the college, and so that they can take the exam later on in the day, I mean at night, I should say, early at night, or those who are working also at night so that they can take care of it in the day. So this is plenty of time to do that. You have already the review on Canvas. The review has been available now for several days. I know some of you received reminders of me again, and you will be receiving more reminders down the road to make sure you complete the review. Review has two important values, I should say. The first one is the fact that it prepares you for the actual exam, which is a long exam, which is kind of requires a lot of work. So you're strongly urged, if you did not start it yet, to complete it. It's going to expire by midnight tomorrow. So I'm hoping that you guys, if you did not take advantage of this opportunity, you start it right now. Okay, this is by far the most urgent thing that you need to do in this class this week, to make sure you complete the review to prepare for your exam on Wednesday. So this is the utmost importance, and it takes precedence over everything else. I know there is a homework that is due toward the weekend, and that takes second stage. The homework has an assignment that is yours required to submit, but you have until Saturday to do it. So if for some reason you think that you have to do, please delay that. The urgent matter at this point is the actual exam, and in that you have to prepare for it. So that is important. That is item number one. Item number two is the fact that that review is actually graded on itself. So in other words, it is an assignment by itself, and that shows me how much you're willing to engage in the classroom and participate in doing what you're supposed to be doing to pass and do well in the class. So the grade for that, basically, there are two grades. Either you get full credit for it or you get no credit for it. The full credit, you get it just by trying and basically doing the actual review. Regardless of your actual grade in the review, you're going to get full credit for it. So that is the value for it. Otherwise, you will get no credit, basically, if you don't do the review. So that's why the review is, at this point, the most important urgent matter that needs to be completed before midnight tomorrow. Now, that doesn't mean if you start the review that that's the end of it. The review is actually has the first value that I mentioned, in a sense of prepare you for the exam. So please go through it again and again, especially if you don't feel 100% confident that you're going to score 100%. Okay, why not? Okay, so if you think that you're going to score 99%, that is actually something that you should take you back and make sure you complete the review. So it is a self-contained assignment in a sense. Everything is contained within the review that should help you prepare for the exam. So this is by far the most important step that we need to be talking about. The other point, which is also important, the lab this afternoon is still on. So we have a lab at 12:45 today. That is still a requirement. So if you don't attend it, of course, you're not going to get credit for it. So please make sure you attend all the labs. Labs are never canceled, no matter what. That's why exams are held actually on Wednesday, so that to make sure that you do your labs on Monday. Having said that, on Wednesday, we will not have a live session because of the fact that some of you, the only time that is available for you guys, if everything else fails, is the time that is allotted for the lecture. So, and under normal circumstances of our meeting on campus, that is what would have happened anyway, that during the exam time, we will not have class, so we'll just focus it and dedicate it to the exam. So that's basically the idea behind it. So I'm hoping that you have a clear understanding of what's going on this week. I already sent reminders and I already sent messages to this effect. So that just to clarify any kind of misunderstanding in a sense of the writing basically in the messages was not clear. So this is what's going on. In terms of content this week, it is not part of this exam, just as much as the content from last week also was not part of the exam. This exam, at least, it is still required for the next exam. As a matter of fact, you noted that the homework assignments were not required to be submitted before last week, but this week and last week, and for the next couple of weeks, also in preparing for the second exam, there is a requirement to submit homework assignments. And the reason is the second exam is different than the first exam. So we're talking about something that is going to happen after Wednesday. The second exam has two components. Has a component similar to exam one, which is basically all of it is just a content-related conceptual exam. That's what it's called. And there is a component of it, and that is to actually doing problems similar to the homework problems. So that's why it's important that the homework from this point on be submitted so that you guys show that you're doing it because you're going to be tested on it. So that's basically the plan for the course. And let me share with you the screen so that we see what we have this week. That's the second most important thing after the exam, of course. So let me share the screen. Let me go back to the course in here. So this is basically where we are in terms of this week. And the only reason I have the week before available is to emphasize for those of you who were not sure where to find the review. It's actually from week 4 when we started the concept of motion. And so that's where you go into your review. So that's so that you guys go. The review is not part of this week's module, which is week 5, but rather it's from week 4. Okay, so last week. The other thing also that you noted there is the homework assignment that is due on October 8th from last week. So that assignment, please do not ignore it. It's still due, but after the exam. I know it was assigned before, so I was hoping that you guys would have completed by then. If not, try to do it immediately after the exam. It's still due this Saturday. Then this week, of course, we have the normal stuff, basically the objectives, the videos. There are several videos in here. There are 4 videos. They total about 25 minutes altogether. So they are short videos, or I mean, 2 of them are like 7 minutes or something. So they're short videos so that you can go sit down and take notes while you're doing that, because they hold in them a quiz. That should show again that you're participating and doing what you're supposed to do. In addition to the reading, and it tells you also which pages you're supposed to be reading. So I can click on one of them. It tells you exactly the concept that you're supposed to be reading from the book, with the emphasis on the working it out. There are sections in the book where it says you're working it out. That shows you examples on how to do numerical stuff. And then, of course, you're going to, this is the summary of the concept that we'll be covering through this week. And then, of course, you have this links. This is 5 minutes and 25 minutes, 7 minutes, 13 minutes, 7 minutes and 59 seconds. And there was I thought there was 1, 2, 3. Yes, there are 3 of them. Yes, 3 of them. And then you're supposed to, at the end, answer the quiz in here, okay? So that is basically the idea behind it. I think there is another video that I'm going to update it for you guys. Again, this stuff is not due now. So if you click on the quiz, it's not due now. So we're not going to be worried too much about this quiz in here. It's only 4 questions in it, so it's not really that long to take. And then you have the discussion from this week, which is due also next week. Okay, so this stuff is not urgent. The lab, of course, we have a lab this afternoon. It has to do with the vector additions. And this is the exam on Wednesday. Okay, this is the exam on Wednesday. You can come in here and you take it. It's not available right now. Okay, because I'm logged in as an instructor, if I click on it, it's going to open. Assuming that it thinks that I want to edit it, but I don't want to open it because it's still available. It's still going to open for you guys on Wednesday. Then you have homework 4. Homework 4 right now, if I open it, I'm going to see it. But if you guys do open it, it's not going to be available until Thursday. Okay. The reason is because this homework is going to be due the week after, 10 days later. So you're not going to really be bothering too much with it, trying to work on it. Okay. Of course, the recordings of this week's session, because there are sessions. Normally, we have 2 sessions a week, Monday and Wednesday. But this week, there will be only 1 session, which is this one. It's going to be posted in here once we're done with that. Of course, the later weeks are not available at this point. But that's basically the plan for this week, okay? So, and again, this is where the exam is, this is where the review is, and this is the focus of the stuff. Having said that, let me stop sharing. Let me go with the content again for this week, okay? Let me share again my notes. And this week deals with, of course, make sure that my pen is writing and my stuff is ready. Let me change the color in here. Okay, it's good. So this week is chapter 3 from the book. And chapter 3 deals with basically 3 ideas: the laws of Newton. Okay, in the laws of Newton, you have, of course, the first law, the second, and the third law, okay? And then the other idea is the concept of the net force. Well, you would need that to apply it in the second law. The second concept that we're going to be dealing with, and that's actually a consequence of the last point in here, which is the force of friction. As a matter of fact, it was this concept that led Mr. Galileo to state the first law, basically, before it was actually called Newton's first law, in the verbiage that it is, what it is what it is today, okay? And the force of friction also is needed to account for the net force. And I will give several examples where that is. Force of friction has several components of it. There is the static friction. There is the kinetic friction. There is the air resistance friction. Okay, that's not the end of it. There are far more to it than this one, but we're going to restrict ourselves to these 3 cases. There is actually the drag force. There are all kinds of other forces that involve friction, okay? And the third concept that we're going to be dealing with, again, it deals with the net force, and that is the vector additions. Okay, so because you're ultimately trying to find the net forces, and here is the case. You have somebody is pulling on something from one side, and another person is pulling it from the other side. So which way the object is going to move? Okay, so you have a box in here, or a container, and 2 people are pushing on it. One person is coming in here and trying to push this way, and the other person is trying to push it in the other way. So that is what these forces are. They represent these directions of these forces. So obviously, you ask the question, which direction the box is going to move to. It's not going to move based on the wishes of the first one, because the second one is pushing in a different direction. It's not going to move in the direction of the second one, because the first one is pushing it in a different direction. So at the end of the day, it's going to move in what is known as the sum of the 2 vectors, which is the resultant also called, and I think that's what we call it in the lab. So that is what the resultant is. The resultant is the sum. It's coming from the word result. Resultant, I'm missing the letter L in here. So that is the resultant of the 2 forces. And that is basically what the idea behind it is. So we need to find the net force. That's also the word that we're going to be using extensively. That is the net force, okay? Except that the resultant usually is a more general word than actually the net force, because the net force really deals with forces, but the sum of 2 vectors can be any 2. Case in point, and I'm starting with the last point in here, you have an airplane that is basically flowing in the in the sky, and it's moving with the velocity in this direction, but the wind is blowing this way, for example. So which way the plane is going to drift? It's going to drift in the resultant. So the plane is not going to go one way, it's not going to go where it wants to go, but it's going to go in the resultant of which way the wind is blowing and which way the engines are actually trying to go. Okay, so that is actually, so it's not necessarily just the forces. So this idea of vector additions goes beyond the concept of net forces, okay? But the net forces are just special case of when we add vectors. So these are the concepts that are covered in here. Historically, of course, we start with the laws of Newton because they're kind of the starting point. One of the items in the discussion in here is, and that's a really important statement, okay? That somebody comes and tell you that you can do everything you want to do in life, in real life, basically solving any mechanical problem in real life, car moving, something falling, you're throwing a projectile, you're trying to stop something, you're playing with a soccer ball, for example, trying to block it, or trying to do all kinds of motion, any kind of motion, the wind is blowing, whatever, the sound, all of these things that you hear and watch and do on a day-to-day business can be explained with these three laws. So everything obeys Newton's laws of motion. Nobody can escape that, no matter who you are, okay? These are something that is kind of general, and that is the idea of the discussion, so that you guys see how you're going to basically argue against it, okay? Okay, so again, there is the first law, the second law, and the third law. But the common term in all of this is the word law. So what in the word is a law first? Okay. So the law in science in general and physics especially, okay, is a proven rule that cannot or can never be violated. Okay, so that's basically what that means. So this becomes a law. So you go and make an observation and something, for example, you take an object and you let go of it, okay? And it falls. And you measure the rate at which it's falling. And you find that the rate of which it's falling, it's an acceleration g equals to 9.8 meters per second. In other words, it's going to gain speed as it's falling for every second at the rate of 9.8 meters per second. So that's what that means. So if it was not moving, that's when you let go of it. So it was at rest. You come after 1 second and you measure its speed and you find it's exactly 9.8 meters per second. You come after 2 seconds of its fall, and this number doubles. So it's going to be 19.8 meters per second. Okay? So every second it's going to gain 9.8 meters per second. So this is your observation. And you do this repeatedly. You do it all the time. To answer your question, Alex, I think it's like 11 p.m. Okay. So again, for those who are watching this recorded, of course, you don't have access to the chat sessions. There was a question about what the exam, when the exam is going to end on Wednesday. The last time you're going to do it is 11 p.m., but do not start it at 10 p.m. That means you started way before, because there might be issues that you might encounter where the internet all of a sudden for the last half of your questions basically goes down, or there is a power outage, or you never know. So don't delay it until that time, okay? Again, so basically this is the idea behind it. So the point in here, you observe this time and time again and again and again and again and again, and you make a statement, you know what, I think this is a law, that this never seems to be violated. Obviously, this condition is that you do it in the absence of air, as a matter of fact, you do it in absence of friction. So in this case, you promote this to a law. So this is what we mean by a law. So the first law was based on the observation of Mr. Galileo, and he did this experiment again, and I mentioned it last time, and actually it's mentioned in one of the videos also. Basically, before Mr. Galileo, people held the belief, based on Aristotle, that the object tend to stay at rest, because if you move an object, ultimately it's going to stop. Therefore, this is what they want to do. They want to stay at rest. So if you move them, they will ultimately come back to rest. So what Mr. Galileo did basically, and I mentioned this one, he took marbles and he dropped them through an incline and he noted where they stop. So what he did is he made the surface smoother, and he did the same experiment from the same height, but he noted that as the surface is smoother, the object tends to stop further down the road. So if he made it even smoother, so he made this all the way further, it's going to stop. So he theorized that basically, if you repeat this experiment time and time again by making this the surface smoother and smoother further until you eliminate the friction, that there is no reason for this marble to stop at all. It's going to continue forever and ever and ever and ever and ever, and impeded until basically the end of time. So this became the first law. Okay. So unless acted upon, by a force, of course, in this case, he was dealing with friction. He got rid of this friction, okay? But in general, unless acted upon by an external force, an object retains its velocity, and the word velocity here is done in purpose, not speed, but rather velocity. What I mean by that is both speed plus direction. In other words, if you see something going around in a circle, or at least making a curve of some sort, part of a circle, that is being acted upon by something. Why? Because its direction, excuse me, because its direction is changing. If you see an object that is all of a sudden speeding up, meaning that it's going further than what it was going before, or slowing down, meaning it's moving with a speed less than what it was going before, then that object also is under some external force, okay? And if you see an object that is doing both, all at the same time gaining speed and at the same time turning one way or the other, then in this case also it's acted upon by an object, by another force. So here is the thing to watch for. Is the speed increasing or decreasing? In either case, in this case, there is an external force, or the direction is changing. Okay? It doesn't matter which way it's changing, left, right, up and down, doesn't matter which way you're looking at it. So in this case, in either of these conditions, there is a net force on the object. This is not the subject of the first law. The subject of the first law, when there is no change to the speed and no change to the direction. Both of them have to be the same, which is in a sense the same velocity, because the velocity is both the speed and direction, which means the velocity is the same. So when I'm talking about an object, you can think of a car, for example, okay, as a practical example. So this is like a car, for example, going with the cruise control on it. This is my, okay. So you have the cruise control, and the cruise control is basically being set to a speed, and that speed, let's say, for example, 50 miles per hour, and the road is straight, and there are no bumps in the road, okay? That's it. That is actually, that is the first law, okay? The second law, the condition for the first law, of course, is the sum of the forces. That's what I mean by the net force is zero. That is what the net force is. I mean, I know in here I said an external force. You could have an external force, but you could have two of them. They are opposite directions, so they cancel out, okay? So that's basically, that's also similar. So if you have two forces, a 5 Newton one side, and another 5 Newton on the opposite side, in this case, if you add them up, it's zero. So it's the same thing as if I don't have an external force, because if I have one and I have paired it with another one that is equal to it but opposite to it, then they cancel, and therefore it's similar, okay? So the net force is zero. Okay, which brings me now to the condition for the second law. The second law says that if the net force is not zero, I mean, we just write this symbol, by the way, when you see it everywhere, that is the Greek letter sigma. There are two Greek letters sigma, okay? There is the lowercase sigma and the uppercase sigma. So when you see the Greek letter sigma, it means the sun, that's all. So don't be too scared of it and think that it's, as a matter of fact, we use the Greek letter symbols a lot. So instead, I could just have called it F net. That's what the book calls it. So probably I should use the same thing. So F net is the same thing. When net in this case stands for add up everything, okay, and find the net force. So the net force in this case is not zero. It's the same symbol in here, whether you use net or use the Greek letter sigma, okay? So that is, and it's good to see both of them so that you don't be turned away when you see it in a different literature or a different book or a different reference we're trying to explore. And then you see the Greek letter sigma and you say, what is that has to do with what we're doing? And that is exactly what the symbol net in this case is. So net means add everything, okay? And the sigma is add everything. So that is basically what these two things are. So in the case when the net force is not equal to zero, so what we have in this case, note that the force is a vector also. Meaning it has direction and magnitude. So when I wrote the 5 newtons earlier, and when I wrote the other 5 newtons with it, I made sure that they are in the same basically axis, but one of them pointing in one way, the other one pointing in the opposite way, meaning that they have opposite directions, okay? So in this case, they add up to zero. So the force is actually a vector too. It's not just the velocity, which is a vector. So there are a lot of vectors in nature, and these are two of them. So when I say the net force is zero, I really mean the vector force, okay, is zero, okay? So that is, you add everything in here. But the vector force is zero doesn't mean much, honestly, because how are you going to draw a vector of magnitude zero? So which way it's pointing, it doesn't make any sense. So it's pointing everywhere or nowhere, because it's a point in space, okay? So in this case, but when we're adding them, we have to be careful and mindful of the fact that these are vectors. Because if I draw 5 Newton this way, and a 5 Newton this way, it's not the same. This is not net zero is zero. The net force is zero. Actually, the net force is 7 newtons pointing this way, 7.07 Newton pointing this way. I have to be careful in here, okay? When you're asking how do they get 7, it's just applying the Pythagorean Theorem, which we're going to be doing in the lab today. The square root of 5 squared plus 5 squared, which is 5 times the square root of 2, which is equal to what? 5 times 1 point something, okay? It's going to be about 7 point something Newton. Anyway, the point being in here is this is not zero. Why? Because the two vectors have directions that don't cancel out. In this scenario, the vectors do cancel out. In here, they don't, okay? And both of them are 5 Newton. Both of them seem to be applied to the same object, but in this case, this results in a net force. This results in a no net force. So you have to be careful of the fact that the force is a vector, okay? So if I have a net force, then in this case, the object will accelerate. So this is basically what the consequence is. If the net force is not, and I probably should underline the word not, 0, then the object accelerates in the direction of the net force, with an acceleration given by, so I'm going to write a mathematical equation in here and talk about it. So the expression is, this is the acceleration, which is also a vector. So there are 3 vectors today that we saw: the velocity, the force, and now the acceleration is just the force divided by the mass. So the term in here that came into play is this m. Here is the deal. If I have, for example, a small box and push it with a force of 10 Newton, sometimes we don't have a sense of magnitude. How much is 10 Newton? You want to know, okay? Is it a lot of force or is it not a lot of force? Okay, I want to know that. So think about it this way. If you take a kilogram, which is roughly about 10 apples, okay? 10 apples, maybe less, okay? Maybe 6, 7 apples, okay? You put them in your hand, that is about 1 kilogram they weigh. That is about 10 Newtons. Okay. A bag of potatoes, the 10-pound potatoes, is about 5 kilograms. That's about 50 Newtons. So just to get you a sense of idea of how much we're talking about in here. So a bag of potatoes, that is, there is basically a 10-pounder full of potatoes in here, okay? And usually there is a place where you hold it when you grab it from the store. So there is a bunch of it here. So this is a 10 pounds. It's roughly about 5 Newtons. Okay, because it's about 5 Newtons, 50 Newtons. Okay, why? It's because about 5 kilograms, and that 5 kilograms times 10, which is G actually, I have made it approximately 10, give me about 50 Newtons. So in order to have a sense of what 10 Newtons is, take that 10-pounder and divide it into 5 pieces, and each one of them is about 10 Newtons. So that's basically not much force, isn't it? So if I have a small box and I want to push it with the 10 Newtons, and let's say for the sake of argument that this box is 1 kilogram, then it's going to accelerate according to this formula with this acceleration 10 Newton divided by 1 kilogram. So this box is 1 kilogram, okay? And the acceleration is going to be 10, of course, it's an acceleration meter per second per second. In other words, it's going, if it was not moving, after 1 second, it's going to be moving with the speed of 10 meters per second. So it's going to move fast. And then after another 10 seconds, it's going to be 20 meters per second and so on and so forth. So it's going to gain more and more speed as it goes. Let's apply the same logic with the same 10 Newtons on a car, okay? Let's say for the sake of argument, the car, which is a lot of car, okay, sitting with no wheels on it, okay, sitting straight flat on, okay, on the surface, okay. So you have the sitting on the rims, okay. You remove the wheels and it's been stuck in there for a long, long time, and it's rusty and dusty and all kinds of problems with it because it's, and you would want to move it, okay. And let's say, for example, for the sake of argument, that this car is 1,000 kilograms. Of course, it's more massive than a small crate. And the only thing that you can afford is a 10 Newton. So the same 10 Newton, you would want to apply it on this car, trying to move it, okay? Because you were successful earlier with the crate, you pushed it with 10 Newtons, and all of a sudden it flew out of the area. So basically, you're good. So if you see the small, you see a car in there, you say, okay, I am Superman, I can do the same thing. It's 10 Newtons. So how much acceleration according to this law is going to give me? It's going to still 10 Newton, but divided by the new mass, which is 1,000. Obviously, the acceleration is going, when you divide 10 by 1,000 kilograms, by the way, when you divide 10 divided by 1,000, it's going to be 100th. And 100th decimal-wise is 0.01 meter per second. So in other words, it's hardly going to budge. After 1 second, you barely are going to see it move because it's going to move by 0.01 meter per second. You wait another second, it's going to hardly, and you have to maintain that 10 Newton, by the way. Because if you let go of it, if F becomes 0 all of a sudden, the acceleration drops. Okay? You get tired. So the fact that you carry, for example, a 10-pounder, imagine you're carrying a 10-pounder. If you carry it from here to here, immediately it's not going to be as tiring as if you carry it for half an hour or something. It's going to be more and more tiring. That's the same idea in here. So you need to really, in order to see an appreciable motion of this car, you really have to maintain it for a long time before you see it moving. So the point in here is this mass, which is the symbol for it, represents the resistance to the change in motion. What do I mean by that? Both the crate and the car did not have motion. They were sitting still. But one of them has more mass than the other. The one that has more mass resisted more to changing its motion, to having it move basically, than the one with the less mass. So if you have less mass, you tend to resist less to the change in motion. So that's why we call it the resistance to the change in motion. So more mass, meaning you don't want to change your state. You would want to stay where you are. Let me give you the example backward, okay, to see. That will probably make more sense, okay? Let's say, for example, I have a crate that was flying across the room at 20 meters per second, super fast, okay? And you would want to stop it. So here you're standing, and this is your hand, and you would want to stop it. I don't want you to move anymore. And the only thing that you can afford, again, is 10 Newton. So in this case, you would want to bring its speed from 20 meters per second to 0. And let's say, for example, you would want to do it in 2 seconds. That's all. Okay. Obviously, you're going at 20 meters per second, and you're going to slow down to 2 meters per second. You could do it with a 10 Newton because 10 Newton, and let's say, for example, this is still 1 kilogram. It's the same crate that I started with earlier. So in this case, you're going to move with this one. The minute it hits this one, it's going to be subject to a force of 10 Newton. So you ask me how much the acceleration is 10 Newton divided by 1 kilogram. And this will result in 10 meters per second. That is going to decelerate in this case, because the object is moving this way at 10 meters per second. I mean, 20 meters per second initially, of course. And then you apply force. You have to apply it this way, because if the object is coming this way, you have to stop it. So you need to move it in the opposite direction. So the force needs to be applied this way. So the acceleration has to be in the direction of the net force. I forgot the net force in here. So the acceleration has to be in the net force, meaning this is the direction of the acceleration that we're talking about in here, the 10 meters per second. Okay. So that is so now you have the velocity going this way of the crate, of course, on the impact, and you have the acceleration in the opposite direction. So this is going to result in the negative acceleration or a deceleration in this sense. So it's going to slow it down. So after 2 seconds, obviously, it's going to decelerate to 0. So the initial velocity was 20 meters per second. And when you add to it the acceleration, which is a negative now in this value, because the direction is positive is this way where it was moving, and I put this one positive. So the acceleration has to be negative, which is 10 meters per second times the time it takes for it to bring it down to 0. So in this case, I just compute and I will find that 20 meters per second per second. That's the initial velocity divided by 10 meters per second per second. The meter cancels the meter. The second cancels one of the seconds. And the 20 divided by 10, 20 divided by 10 is 2. And then when I divide by 1 over the second, I'm going to find it in 2 seconds. So indeed, it's going to stop in 2 seconds. So good. I was successful in blocking a mass of 1 kilogram with just a bare hand that a force of 10 newtons. Can I do the same thing for a car? Obviously, don't try this experiment at home. It's going to hurt a lot. It's going to be actually deadly. Don't do it, okay? So if I have a car, okay, moving with the same speed, okay, 20 meters per second, by the way, is a lot of speed, okay? So it's moving in this direction. So I probably should have bumped in this way, okay? So it's moving in this direction. So this is the driver, and this is the wheel and all of that, okay? So it's moving in this direction. It's moving also with 20 meters per second, the same thing like the crate does. Now it has wheels because it needs to be moving, okay? And let's say for the sake of argument that this thing is going, it has 1,000 kilograms also, as we just before. It's the same car, except now it's fixed, okay? Or before it went damaged, okay? Anyway, the point being in here, and that's the only thing I could do, is try to stop it with the same 10 newtons. Of course, don't do this, okay? If you're gonna, I hope that you know that it's not gonna work, okay? It's gonna hurt a lot. And you will see mathematically why that is. You see based on the laws of Newton why this is not going to work. Okay, so again, I would want to stop this thing in 2 seconds. Could I do it with 10 newtons? Obviously, let's see what happened in here. The acceleration in this case is going to be, again, the velocity is this way, the acceleration is going to be this way, and I want to stop this one in 2 seconds. Could I do it? The acceleration in magnitude only is going to be the force, which is 10 newtons, divided by the mass, which is 1,000 kilograms. Obviously, this is going to be 0.01, except it's pointing in the opposite direction than the velocity, meter per second, of course, meter per second squared. Okay. Well, if I apply the same thing in here as before and see how long it's going to stop, or at least after 2 seconds, its velocity is going to be the acceleration, which is negative 0.01 times the time t plus the initial velocity, which is 20 meters per second. After 2 seconds, this is going to be 0.01 times 2 seconds plus 20. This is going to be negative 0.02 plus 20, and the answer, if you put it in a calculator, is going to be 19.98 meters per second. So it's going to be moving still, practically with the same speed, okay? So your hand is going to be damaged beyond repair, so don't try it, okay? So in other words, it's not going to work, okay? Why? This has 1,000 kilograms, this has 1 kilogram. The 1,000 kilograms resists the change in motion more than the 1 kilogram. The 1 kilogram, after 2 seconds, it gave up and stopped. This one, after 2 seconds, kept on going with almost the same speed, okay? 19.98 or 20 meters per second is the same thing. So barely noted that it's dropped by so much, okay? So it's not going to stop at all. So it's going to continue and continue with vengeance, okay? Because it has more mass. That's what the concept of mass is, and critical in this case. We call this mass inertia. What does inertia mean? It's the resistance to the change in motion. So when you hear the word inertia, you have more inertia or less inertia. It is a resistance to the change in motion. It happened to be the same as mass. So inertia and mass are the same. This is the resistance to the change in motion. And this is how much stuff you have. Stuff or matter, let's put it. The amount of matter, okay, in an object. They happen to be the same quantity, okay? We're not going to talk more about this one in here, but down the road is going to be an issue when we start talking about general theory of relativity, because this was a puzzle. Why the two quantities are the same? Of course, this one is coming from the weight that you can measure. the weight is equal to mg, and this one is coming from the force equal to ma, which is coming from this expression. I mean, when you write it this way, A equals to F over M, it's the same thing as saying F equals to ma. Okay, it's the same thing as writing it this way. And the weight, by the way, is also a force. So the weight of an object, you take it's really, you put it against the force of gravity, and the force of gravity will pull it toward the Earth with an acceleration g pointing toward the Earth. So the weight of the object is also pointing toward the Earth, and it's equal to how much stuff it has, the mass, times g in this case. Okay, so okay, you go and say, you know what, I want to go to the moon. Can I have the same weight? No. So on the moon, the weight, so this is on the moon, the weight is equal to m times g of the moon. Okay, it's going to be less. That's why you saw the astronauts when they went to the moon, they were easily jumping and moving around. On Jupiter, I mean on should I say Mars, it's going to be actually slightly more than that of the moon, but less still than the Earth. Okay, because the gravity on Mars is less than that of the Earth. If you saw the movie, basically The Martian, that's when what's his name? Matt Damon was trying to escape the planet. So he had to deal with the gravity and his own weight, which is really in that case slightly less than his own weight on Earth. Okay, but still more than the weight of the astronauts on the moon. If you are on Jupiter, and I started to mention that, so I have to continue that, on Jupiter you would weigh more. So again, it depends on the force of gravity, and it depends on the mass of the object that you're trying to escape, and it depends also on the radius of that planet and so on and so forth. And we're going to discuss that down the road when we talk about the force of gravity in more detail, gravitational pull. Okay. So this is an example of a force actually that you're going to be dealing with. Okay, so the force, one of the forces that we're going to be dealing with is the force of gravity. And the force of gravity always points toward the Earth. Okay, but if you're standing, okay, if you're standing, the force of gravity is being pulling from your center of mass, of course, toward the Earth, and but you're not falling, because you're standing on the floor. So what happened in this case, there is a force in this case that the floor will exert, and that is the normal. So this is another force that the object will exert on you. And how much is the normal? That brings me to the third law of Newton. And the third law of Newton, if you have two objects, here is the floor, and here is you. So you need two objects for the third law of Newton. I mean, two objects, yes. If one of them exerts a force, which is in this case the person you exerting a force, and where is that force is coming from? It's coming from the Earth. It's trying to pull you down. Okay, so now you can't go anywhere, so you have to go through the floor. So you have to push on the floor. By how much force? By your own weight. Well, the floor in this case is going to exert a force that is equal in magnitude and opposite in direction. If two objects, that's what the third law. So you really need more than one object. If two objects interact, that's a condition, because I could have the floor in here, and it could have you, for example, falling from a higher elevation. So you still have two objects. You have the floor in this case, and you have you, but you're not interacting. There is no interaction. So you really need the objects to interact. If two objects interact, and one exerts a force on the second exerts an equal force. So it has to be the same value, but opposite in direction. An equal but opposite force on the first. You need them interacting, okay? If they're not interacting, forget about it. In this case, you and the floor are basically interacting. And in this case, if you push on the floor with one force, the floor will push on you with the same equal amount of force. That's basically, but the two forces are in opposite directions, okay? This is sometimes referred to as action-reaction principle. But that's it. That's all the 3 laws of Newton. That's all the 3 laws of Newton. They're simple, effective. So if tomorrow police officer stops you and he tell you, why did I stop you? Tell him why. Tell you because you're in violation of the law. That's what he says. You tell him which law, the first law, the second law, or the third law. That's only the 3 laws that we know of. Okay. Obviously, he's going to mention some other nonsense laws in the books and all of that. I don't want to say nonsense, but the laws that we agreed on and called laws, but those laws are violatable in a sense that, for example, if the speed limit that is posted 65 miles per hour, and when no one is looking, make sure that there is no one around you, you could actually go to 66 miles per hour and nothing happens, okay? You could violate it. Okay. Make sure nobody's looking though. Make sure you're alone in the road and nobody's in there and no animals, no nothing, so that nothing can get hurt. But if you go 1 mile above the speed limit, you could violate that law. Okay. There's no harm in it. I mean, at least if there are no cops around. When there are cops around, they will give you a ticket for going over the speed limit. But these laws, you can do that to anything with them. Nothing can violate any of these laws. If an object and there are no net forces, there is no way it's going to change its velocity in magnitude or direction. End of the story. You cannot violate that law, period. So the first law will apply all the time. Nobody can come in here and tell you, hey, I'm going to ticket you for for violating law number 1, because you can't. Nobody can. Unlike the other law that's over the speed limit, which you could do. I mean, don't do it, but you could theoretically. That's why people get stopped and get tickets for it, because they violate. Sometimes they go even more than 1 mile per hour more than the speed limit. So the point being in here is those laws can be violated. So they should not really be called laws, at least scientifically. So they are not laws, okay? Because they can be violated. These ones you can't. Same thing. Now, if the net force is not equal to 0, the resultant, the immediate consequence of that is that an object will be changing its velocity either in magnitude or direction or both. And how much acceleration is going to get? It's going to get this acceleration, which is given by this law. There is no way you can violate this law, as long as the conditions for it are true. Namely, the net force is not 0. If the net force are 0, then you go back and resolve back to law number 1. So you are either between law number 1 or law number 2 if you have a single object. If you have more than an object, then you ask a question. Are these 2 objects interacting? If the answer is no, then back to law number 1 or law number 2, depending if any of these 2 objects has a net force or no net force. You're in good shape now. You're done. Now, if you answer the condition for this law is true, namely that these 2 objects apparently are interacting, oh, then the 3rd law will apply. There is no way you're going to violate that law, 3rd law at all. So again, no police officer will stop you and tell you that you're in violation of the law, because you can't. Okay, you can't. Any of these 3 laws will always apply to you. So again, if a police officer asks you that you're in violation of the law, tell him, sir, I think you are mistaken. Nobody can violate the law. Okay. Obviously, you have to ask him which law you're in violation of. He can't answer the 1st law or the 2nd law or 3rd law. Obviously, he can come and answer what he calls a law. Then that's an issue that you're going to resolve with him in court. Okay. And I don't suggest, honestly, to be argumentative with him or her, because you might get in trouble. So don't do that. Okay. Okay. So don't take my words literally for that. Okay. But this is the emphasis on this thing in here, so that you guys understand the value of this laws. And that is the item of discussion that is actually for this week. Okay, so hopefully we have a clear understanding. I know the videos that I posted have plenty of discussions in them, so hopefully you guys can go through them also. And which brings me to the force of friction. Here is the scenario. I'm sitting in front of a desk right now, and I'm actually we're going to demo stuff like this one in the classroom today in the lab. So I'm going to push on an object. Actually, the object is not moving. Okay. So in this case, here is the example. if you have a crate, for example, let's give it a little bit more mass, okay, than the first crate, okay? But let's make sure that it has more stuff in it. Fill it up, okay? So let's say, for example, for the sake of argument, this is a 100-kilogram crate, okay? About the refrigerator, for example, or something in the kitchen. And try to push it, okay? And again, all you afford is a 10 Newton. Obviously, and that brings me back to the example of the car earlier that I did, which was an important example. I'm assuming that there is the surface in here is as smooth as possible. That's why it results in this acceleration. In a practical example, if you try to move a car that is actually, even with wheels on it, with 10 Newton is not going to budge at all. Why? Because there is friction. Same thing in this case in here. So this math in here assumes that you have no friction. So this is a frictionless surface. Now, if we introduce friction, the problem even gets worse than the first big problem. So not only you're not going to get 0.01 meter per second, you're not going to get that at all, unless you apply tremendous force in here to budge this thing. So 10 Newton is not going to do this example at all on a real practical example. So the car is not going to accelerate, period. Same thing with the crate, which is about 10 times less than that car, because 100 kilograms is less than 1,000 kilograms. And they're practical examples, and there's a non-smooth surface, a regular surface, this object is not going to budge. So when you ask yourself, hey, wait a minute, didn't we say the net force? If I have a net force, external force, there is an acceleration, and that acceleration in this case should be F over m. So mathematically, this should be 10 Newton over 100, and this should result in an acceleration of 0.1 actually meter per second. So 0.1 meter per second squared. So what happened in this case is you have another force that is in the opposite direction. So I'm pushing, it's not moving. So I must have another 10 Newton in the opposite direction. Okay, so that the net force is actually 0. So this number is actually 0. And when I divide 0, so there is another negative 10, if you wish, to add up to 0. And that will result in a 0 acceleration, not this number. The same thing for the car, by the way. In a practical example, you're not going to even get that 0.01 meter per second. So in this case, I'm not going to even get that much. And that force is the force of static friction. Okay, so 10 Newton is not going to do it for me. How about if I double the force? Okay, 10 Newton is not going to do for me. So I'm going to make 20 Newtons. I'm going to push more. Okay. If the crate has mass enough, and if the surface contact is made up of a normal stuff, even this one is not going to do it. So you ask, what happened? Wasn't it the net force was the friction was 10 Newtons earlier? Well, it's adjusted, it varied. So it went to 20 Newton now. So the static friction is not constant. It changes. It increases with the applied force. The more force you apply, the more the friction will be. Until at some point the crate will move. If you have the applied force above a certain threshold, at that point the friction will give in. That's it. It reaches the maximum value. So the applied force keeps on increasing. You keep on pushing. Of course, you could tip it, okay, especially if you're not pushing in the right direction, in the right point, depending on the center of mass. But if you're pushing it in the right place, you could keep on doing it until it gives in. So the friction, the static friction is not constant, it changes. So if you apply no force at all, so here are the graph, okay, that might exemplify this point in here. So this is the applied force. If I apply no force at all, I get no friction. So if the desk right now is not basically being pushed, there is no friction to oppose my push. Otherwise, it's going to move under that force, okay? And then, so this is the friction. The minute I apply a little of force, the friction appears. The static friction, that is. I apply more, more appears. I apply more, more appears. I apply more, and then something strange happens. It gives in. So up to a certain critical value, I'm good. And then it starts moving. And when it moves, then I really don't need to apply the same force. At least that's what the experiment had shown. The object will start moving. So this is not static anymore. This is kinetic friction. Okay. So kinetic is friction when the object is moving. Static is when friction when the object is not moving. So the object not moving, and kinetic object is actually moving. Let me be upfront and tell you this, okay? This is one of the hardest subjects that physicists deal with. This is not easy, even for the most advanced people to really do these things in here, but it is necessary to understand these things. I know it's kind of hard, especially in this class, we're not going to be doing with a lot of math. I know some of the homework problems I assigned have 1 or 2 examples dealing with friction. So when it comes to the example, it's just another number, that's all, okay? But the point in here is you have these 2 kinds of friction. There is a third friction that we're going to briefly mention in this case. And we alluded to it when we were talking about the force of gravity earlier. If I drop an object, and that object's in here, meaning that there is no air resistance. So if there is air resistance, there is friction, and this number changes. That's why if you do the experiment, for example, you take a feather and you take a hammer and you drop them in the air, in the normal air, obviously the hammer will fall to the ground first, because it will basically overcome more the force of gravity, the force of friction, because it has gravity, and that gravity will pull it down. And the gravity is the same both for the hammer and the feather. It's the same 10 meters per second, but the feather will basically encounter the air resistance and will fall ultimately to the ground, whereas the hammer will fall straight through. Okay. But if you do the experiment in the vacuum where there is no air, then in this case, both of them will drop at the same speed. Doesn't matter. So that's why you have to be careful in here. So that's the other friction, and that is friction, actually, resistance of the air. So that is actually another one. So the other one is air resistance. Is a form of friction. Okay. The math for it is complicated. Just to say the fact that it is proportional to the speed. Object is moving, will have air resistance. Object is not moving, take a feather and you put it, there is no air resistance. If the wind is blowing on it, that's another problem. But that's basically what we're talking about in here. Note that friction in general has to do with speed. Friction in general has to do with speed. Okay? That is really the secret behind friction. Friction relates to speed. When I say the word speed, it's intentional. Okay? Speed meaning v not equal to 0. Okay? Granted, there is a static friction in here that deals with an object with no speed, but again, that deals with v equal to 0. Okay? Because you would want to ask the question, what is the direction of the force of friction? And the direction of force of friction is always opposite to the direction of the velocity. But in here, the object is not moving. So which way the friction is pointing? That is the intended direction of motion, because you push an object this way, and the object, if it were to move under that force, is going to go in that direction. So what it does in this case, it opposes that. So it's going to apply force in the opposite direction of the motion or the intended direction of motion. So there is, even in the case of the static friction, there is that concept of velocity involved. Okay. I think enough said about the friction. Friction has a bad reputation in physics, that to the point that even physicists, they call it the bad boy of physics, because it really complicates stuff for us a lot. And practically, it's an important concept. Since we're talking about cars, what makes your car move to begin with is the friction. You have the wheels. This is one of the 4 wheels of the car. The engine, all it does, the engine, is make the wheel spin. That's all. So let's say, for example, the spin of the wheel is in this direction. So now the wheel is in contact with the ground. What the wheel does in here is going to push on the ground. The ground will push it in the opposite direction. Okay, so it's going to provide a force in the opposite direction with which the wheel is spinning. So in this case, the car will move forward because of the force of friction. So what really makes your car move is the force of friction. You might be suspicious of that, and you say, okay, how come that is? Okay, well, no big deal. Just put a lot of oil on the ground, or make icy road. Okay, I know it's not an experience that we have a lot of it in here in Southern California, but if you happen to be in the Midwest, this is something that happens a lot in the winter, where the road become icy and the car will spin for nothing. So you can turn your engine and crank it for very high, as much as you can, and the car barely moves on the ground because there is no friction. What really makes the car move is the friction. Okay, so it's something useful. As a matter of fact, you cannot move without friction. If you try to move, you have to push on the ground, and the ground pushes you forward to move forward. Obviously, there is another thing involved, and that is your center of mass. Okay, you have to lean forward to change your center of mass also to help you move. But again, for a car, you can do that. The car is basically sitting still. So in this case, what you do, you're going to spin the wheels, and that's what the engine does. All it does is make the wheels go around, and when they do, they make friction, and that's what causes them. I mean, they interact with the ground through the force of friction, and the ground pushes them forward. So that is basically the idea behind this one. So the causes of the car moves by the force of friction. That's what causes us to move. So it's an important concept, and the talk of it, honestly, will never end because there are so many issues with it. There is a viscosity, there are all kinds of other things also that involve friction. So enough said. Okay, the last point of this chapter is actually deals with the sum of forces, and I already alluded to that when I talked about the example for this example. For example, when the 2 forces are in opposite directions, then in this case they cancel. When the 2 forces actually are in on any other directions, we have to use a little bit of something called the Pythagorean Theorem. I know I don't say it with the proper accent because I learned it this when I was young. Pythagorean Theorem, I learned it in French, so it stuck with me. Okay, it sounds kind of different when I say it differently. So again, these are 2 forces, you add them up, basically, and that's the resultant of them. So that's basically what the concept of the forces. But let me give you practical examples that are related to the homework so that we can do them. So if I have a 3 Newton, and if I have a 5 Newton pulling on an object in this direction, in this same direction, so obviously the resultant in this case is going to be the sum of the 2. It doesn't matter which direction you're going to choose. It's nice to usually find where the bigger value is and say, this is the direction that I'm going to make positive, meaning the 5 is positive and the 3 is negative. So in this case, if I add the 2 numbers, it's going to be 5 minus 3, and that is 2 Newton. So the net force in this case is equal to 2 Newton in this direction. Since I just mentioned the fact that you could choose your direction every which way you like, this is the 3 Newton, the same example from before, and this is the 5 Newton, and you might be saying, okay, why don't I choose it this way? You could, there is no objections to you. Then you ask, okay, what happened to the net force? Didn't you say it's 2 Newton in the positive direction? It's going to be 2 Newtons also in the positive direction? No, the answer is going to be in the negative direction. So the 5 Newton now becomes negative 5 Newton, and the 3 Newton becomes positive, and negative 5 plus 3 from algebra, it's negative 2 Newtons. And negative 2 Newtons, meaning that the object is actually in the opposite direction, subject to a net force that is negative 2 Newtons. So it's still in the same direction, the force, whether you choose the positive direction this way and you call the force the net force positive, or you choose a positive direction this way and the net force becomes negative. So it stays in the same direction, okay? Obviously, if the two quantities are the same, it doesn't matter which direction you're going to choose, you're going to find zero, okay? So this is one point. The second point in here, when I have the two forces in directions that are perpendicular. Those are the two practical examples for our problems in the class. So in this case, I have 3 Newton and I have 5 Newton. And I ask which direction the force is. Obviously, because the 5 Newton is more than 3 Newton, the force will be closer to the 5 Newton than to the 3 Newton. So in other words, if this is east and this is north, this is a terminology used a lot with the airplane navigations and things like that. So you have east, west, north, south, and so on and so forth. Okay. So which direction then in this case the force is going to be? It's going to be mainly north compared to the east, because if I add the two vectors. So what do you do in this case? You go to this is the start, this is the tip of the 3 Newton. You go to the end of the 3 Newton, the tip of 3 Newton, and you start from there drawing a parallel line to the 5 Newton. So you take the ruler and you measure the distance in here, and you measure the same distance in here. And this is my 5 Newton represented from the tip of the first one. And you start from the beginning of the first vector to the last one. So you could draw it. And that is by construction. So you could find the net force in this case by construction. All you have to do is take the first vector, in this case, the 3 Newton, and go to the end of the first vector and draw the second vector equal in magnitude and parallel to the first one. So the fact that the 5 Newton is represented in here, it's the same 5 Newton. So a vector really has two things, a magnitude, and the magnitude in either case is 5 Newton. And has a direction, and direction is north, whether you're looking here or here. So plus direction. Since both of these two vectors have the same magnitude, which is 5 Newton, and both of them are pointing north, having the same directions, whether I draw the 5 Newton here or on the object, it's the same force. So now I can just go from the beginning of the first vector to the end of the second vector, and by construction, I have found my net force or resultant. So if I scale my graph correctly, all I have then to do is take a ruler and measure the length of that vector and tell you this is how much, whatever the ruler gives me, I scale it up back again. So I probably need to scale down first and measure what the ruler gives me, then scale up to find the real stuff. So this is by construction. Another method, so the ruler will give me a net force in here. Did I give the bad example? I'm sorry, I gave the bad example, okay? Because it's gonna make life a little bit complicated, okay? I should, instead of saying 5 Newton, I should really have 4 Newton. And you will see exactly why I'm saying that, okay? So please ignore this 5 Newton all around, okay? So obviously the net force will be -1 in here. It's going to be 1 in here because 4 minus 3, that's what it should be 1, okay? 4 and 4. And you will see shortly why that makes more sense, okay? At least, I mean, 5 and 3 will work, okay? So, but you need a calculator for it, and I don't really think, but we'll do it on a calculator. How is that, okay? So 3, let me redraw the stuff again. So this is the example I intended to give. It's still 4 Newton in here, and it's still 3 Newton in here. The force is still mainly in this direction. So that is gonna be by construction. So what I have to do is measure that and basically find my force. Okay, here's the trick now to do it without, so this is 4 Newton. There is something that you guys learned from your geometry class a long time ago, and that is the Pythagorean theorem. So the net force in this case, squared, which is the hypotenuse in this case. This is the adjacent, So this angle, of course, I'm looking at it from this angle. And then this is the opposite. Well, if you guys remember, the hypotenuse squared is equal to the adjacent squared plus the opposite squared. I mean, you probably remember it as c squared is equal to a squared plus b squared, where this is a, this is b, and this is c. Okay, so if I take a right angle triangle, and it is a right angle triangle, this is a 90-degree angle. So in this case, if I take a right angle triangle, this is a 90 degrees, this is a, this is b, and the hypotenuse is always labeled as c. So this is a squared plus b squared equal to c squared. So this is the Pythagorean theorem. So in this case, the net force, which is actually the hypotenuse, which is c in this case, is equal to a, and a in my example is 3 newtons. So it's 3 newtons squared plus b, which is 4 newtons squared. Obviously, 3 squared is going to be what? 9 squared. And 4 squared, that's 4 times 4, which is 16 newtons squared. 9 newtons squared and 16 newtons squared is 25 newtons squared. That's why I changed the number so that I can make the square root easy. Okay, so the net force in this case is, using the Pythagorean theorem, is equal to the square root of 25 newton squared. Then when I square root 25, that's 5. When I square root newton squared, that's newton. So the net force now, by calculation using Pythagorean theorem, is 5 newton. And that's what you would do when you scale the system up and down. If I did it with this example, the original example, 3 and 5, this is the same analysis. The net force in that case, in the first example, that I scratched, namely 3 newton and 5 newton. Well, the net force is going to be square root of, again, 3 squared plus 5 squared. And that is going to be equal to the square root of 9 plus 25, and 9 plus 25 is 34 squared. 34 newton squared, I'm sorry. So that's why I didn't feel to do it with a calculator. So let me pull a calculator in here quickly to see what is square root of 2, because it's important that you guys need to know how to do these things, because in an actual exam, you might be forced to get a calculator, okay, so it can do square roots. So let me stop sharing. Let me share, I should say. I stopped already. Share the calculator. So what I do in this case is I have to use the square root in here at the end. And this calculator, this is a scientific calculator. So let's make it a standard calculator, okay? Small calculator, don't have to really. It has also square root at the end in it. So what I need to do, again, I need to take 3 squared. Here is 3 squared, that's 9, good. And 4, I mean, was it 5 squared? That's 25. So all I have to do to it is add 3 squared, okay? So that is 34, okay? Of course, the newton squared is not going to be entered in a calculator. We just enter the numbers, okay? So what I want to really find is the square root of 34. Square root of 34 should be close to 6, but less than 6, more than 5, okay? Because 5 squared is 25 and 6 squared is 36. And this number is just barely under 36, 34. So it should be something like 5 point something close to 6. So the square root is 5.83. So if I did that with a calculator and stuck with my first example, I would have to deal with this decimal number, which is fine, okay? If I use the ruler by construction, I could have done it and find it on the ruler also to be, when I scale it down or up or whatever scaling I'm using, I'm going to find 5.83. So that's really the bottom line. So let me stop in here, share my notes. So again, at the end of the day, that answer should be 5.83 in Newton. So if I stuck with my first example, instead of doing it this nice example in here where everything is an integer, instead I will have this decimal point. That's all. Okay, that's really the difference in that. So these are the stuff that is covered in this chapter in terms of concepts. Okay, please make sure you read those things and do the working it out. It's similar to the stuff that I've been doing. Okay, so it gives you more tools actually to understand what's going on. Again, we're not meeting this coming Wednesday. We're going to meet again on Monday. Monday is going to be a special day because of the fact that we're going to introduce new ideas. But before we do that, we're going to come back to homework number 4 and discuss homework number 4 because we're not doing the we're not doing the examples this week because we don't have a session this Wednesday because we have an exam this Wednesday. Okay, so I look forward to see you guys on Monday. And if you guys have any questions, please let me know. Sounds good? Okay. Well, please take care of the review. Thank you. Thank you, guys. Please make sure you do the review. That is by far the most important thing this week, and prepare for the exam because it has a lot of weight on your overall grade. So that takes precedence over everything. If you have any questions, guys, please do not hesitate. I will try to make this video available to you guys as soon as possible, hopefully before the lab. Thank you.